So we will start. Please to open the first out of 4 session remote sensing framework of the 8th PDD conference. This session is dedicated to Nathan Levi, who was Tarin's, Yaron, my student, our supervision. Nathan was unexpectedly passed away 2 months ago in India. Nathan's parents are our guest of honors at the conference, sitting among us. Thank you so much for joining this special session. I've known Nathan since his bachelor's degree. He attended 2 of my courses and stood out above all other students. Consequently, I was glad he was decided to continue his master and later his PhD under my. Nathan was an outstanding student. He was diligent, excellent, motivated to achieve his goals. Nathan always made all necessary efforts to obtain the best results. In Hebrew, there is a phrase, "Kol melamdai iskalti." It means that even a professional, experienced person can study from his students. This was the case with Nathan. I was impressed by his skills, knowledge. He was able to teach me a lot. Nathan was supposed to complete his PhD studies within a few months. The title of his thesis was using hyperspectral remote sensing for the detecting and mapping soil quality under various land use in drylands. Nathan has published 3 papers in high-rank international journals. Hence, I'm happy to tell you that the Dean and Director appreciated Nathan's research and achievements. And yesterday, the University Senate awarded Nathan with a doctoral degree. No doubt that Nathan deserved this degree. So this is a little we can do. Last September, these are the 3 papers that published by Nathan. Last September, Nathan presented part of his research at the international conference in Potsdam, Germany. The title is Assessing the Land Use Effort on Soil Quality Based on Imaging Spectroscopy in Drylands. Today, Tarin will present it on Nathan's behalf.
I'm very sorry to hear about this passing away. Very sorry to hear about your young guy passing away like this with all the results coming out after death. Thank you very much. And I go out to. I have met him. I was here last time 5 years ago, and said it has been private, but maybe at some meeting. This is familiar. So I work at NASA headquarters in Washington, D.C., a place where the science is not made but administered. give money to do the science, which last 23 years of my life. Before this, I was a scientist at NOAA. We will look now what kind of things we see from space in my program that is called Land Cover Land Use Change program. One of the programs at NASA headquarters under Earth Science Directorate, in that NASA is launching satellites, space and moon and so on, but there is a huge directorate, Earth Science, and this is a slide shows that we already have a global distribution of cropland extent over the world, and it's changed during the past 20 years. And below, you see also the percent cropland in dry land out of all croplands, and you can see also the majority of those places are in Africa, Asia, and in the world it's almost half. On the right, you see global estimates, and that's very, very much. So these are estimates of global cropland areas. And this is a map showing global cropland by irrigated and rain-fed croplands. So you can see in colors where the cold colors, starting from blue to light blue, irrigated crops. And you can see the majority of them are in Asia, South Asia, Southeast Asia, some in the United States, and some in South America and Africa, but most of it, I would say, Asia. So drylands of the world. Actually, third of world population is in drylands. That's why very important to study. And in those areas, there is strong competition for water resources. 24% of global agricultural lands are located in drylands, mainly in Africa and Asia, as I should point. And supplies 60% of the world's food production. And demand for food is increasing continuously. With the first slide you saw and the previous stuff was because of population growth. The food production in drylands is threatened by water shortages, climate change, land degradation, and poverty. Dryland extent is shown here, and you see that the extent is a lot in sub-Saharan Africa, and the second is Asia. What are the issues? People already know all this. I'll just go quickly. That the issues in the world arid zones are environmental degradation, erosion, salinization, with organic carbon pool, conversion of natural and extensively used systems to agricultural ecosystems, which lead to mineralization, depletion of organic carbon pool, emission of CO2 from soil, soil degradation, which helps lead to pollution. Now, a little bit about the program that I manage at NASA headquarters. We reached our 25th anniversary. It was a big milestone. A couple of people from here participated in our science team meeting in Maryland a couple of months ago. So during these 25 years, we've had over 300 projects with over 800 researchers involved, with over 1,000 publications. The program is truly interdisciplinary because it involves not just physical science with remote sensing, but also socioeconomic science. And the vision is to develop the capability for periodic global inventory of land use and land cover from space. In roughly, the content is shown on the left down there. The third is about monitoring and detection. Another third is about consequences or impacts. And another third for other things like synthesis that we're doing now, and will be other things. So that's what I wanted to emphasize, that human dimensions is an important role on carbon land use change because of the second part, land use, because land use involves humans. So this research includes impacts of changes human behavior on land carbon use change, impacts of land carbon use change on society, and adaptation to climate, which also land use system. NASA has been operating over 50 years now in space. And what is circled here are those particular systems that are most relevant for studying land cover land use. You can see here Landsat systems, Terra and Aqua, fourth resolution sensors, Vermote, ISTAR, future satellites. It's NASA with the India collaboration. NPP, a system that is a kind of continuing legacy of HRR to MODIS and then years on SOM NPP. So these are the most relevant missions that provide us data that we can study and cover. So I just mentioned Landsat 5 and 7 previously. Currently, Landsat 8 and Landsat 9, most recently launched was in 2021. SOM NPP, as I said, is most resolution sensor views as well as MODIS on Terra and Aqua. ASTAR is a Japanese sensor on Terra that provides thermal infrared data. In addition to systematic missions that are listed here, we have exploratory missions that, for example, shuttle radar topography mission was launched just for 1 year that provided us with a global map of topographical map that is being used extensively for correcting Landsat data for geodetic purposes. And Earth Observing EO1 had the predecessor of Landsat 8 called ALI, and also the first hyperspectral sensor in space called Hyperion. And then there are also some instruments on the International Space Station, like EcoStress with thermal IR channels, LiDAR, JEDI, and this is a hyperspectral German instruments, all deployed in 2018 on International Space Station. Since we have different kinds of optical instruments there, they could be used synergistically. They all provide something. For example, these coarse resolution sensors like VIRS, HRR, MODIS, they are, of course, they have a wide swath. They provide global coverage every day or every 2 days, whereas moderate resolutions like Sentinel-2 from European Space Agency or Landsat 8 and 9 from NASA and USGS are much less frequent. With 2 Sentinels, 2 in space, we get repeat 5 days. With 2 Landsats in space, we get 8 days. But if you're not like in Israel, the cloudy regions just may not be lucky enough to get observation sometimes for a whole month. But if you use them synergistically, you may want to find something using this coarse resolution in terms of monitoring, then zoom in with moderate resolution, and then to validate what you see, you use commercial system with Planet Lab data or Maxar data that are already resolution is very high, in 1 and 3 meters spectral resolution. Now, Planet launched over 200 satellites. So now they have really global coverage daily. The major problem is calibration between this 200 something satellites. Every sensor will be intercalibrated so to get something compatible. That's where the problem is. But I think that's the future. Micro satellites observing daily, 1 meter, or everything else will get obsolete. But what you get is from Landsat is a time series for 50 years. Landsat celebrated 50 years in space now. So that's very important for climate studies to be done. as well as HR, also for the 20 years now. What are the projects in the program that I manage on drylands? I will focus on several of them, but I may not have enough time to talk about each of them. So here we have, I tried to pick up almost all continents. First is a West African project by Chris Ney at NASA Goddard. And, we look at hotspots where climate change is rapid and has some high societal relevance. And so that's in mostly Senegal, and their goal is to quantify changes in extent and intensity of irrigated rice and dryland agriculture, and testing the neural networks on very high resolution data for extracting croplands and regional scale. So they use Worldview, or it's a Maxar company, Worldview 2 and 3 images of 2-meter resolution, and SAR is radar data with Sentinel-1 radar. Harmonized Landsat Sentinel-2 time series data were also have been developed during past couple of years, where both streams from Landsat and Sentinel-2 were harmonized in terms of atmospheric correction. And this is the way they develop model. Next is East Africa. In East Africa, we have a project that was just recently selected for funding with Peter Holsky from Montana State and Nina Brooks from University of Connecticut, looking at emerging agriculture humid heat islands. Now the goal is really to look at the impact of heat stress on health. But on the way, they try to identify the regions with greater than 50% increase of short vegetation within HR data, map increase in dangerous hot humid days. That's what affects the heat stress. Locate areas where dryland converted to short vegetation, locate irrigated agriculture. And you can see from 2011 to 2016, the appearance of this field agriculture, that's chiefly center pivots, and how much did added moisture from agriculture increase dangerous hot humid temperature. We don't have results yet, but this is the project. In Mexico, we have a project by Mega Jane from University of Michigan. There was the area where semi-arid areas are. Farmers believe that rainfall is decreasing, droughts are increasing, resulting in negative impacts on maize yield or corn yield. Farmers may adapt by shifting planting date and adopting shorter duration maize varieties that reduce negative yield. These are the areas shown as a function of production. Where 5% of farmers believe weather changes are reducing. Now, going to another continent is India drylands, also the same PI, Mega Giant. It shows this box where the study is done, where there is the semi-arid areas. Much of heart of India main breadbasket lies in semi-arid regions. And in these regions, farmers primarily depend on groundwater to irrigate their crops. Groundwater is becoming rapidly depleted. Future food production will substantially decrease if farmers lose access to unsustainably used groundwater. The main study. That's where the loss with no replacement. You see in color that in red where the tallest year, the color that's showing where there is a loss. Going to another continent, South America. PI is a principal investigator is Song University of Maryland, looking at Gran Chaco region. It's in eastern Bolivia, western Paraguay, and northern Argentina, where the biome where soybean plantations has been growing rapidly. And you can see on the graph how fast they are growing. Soy area in Chaco increased from 2 million to 3 hectares. And during this past 20 years. And so it was really a big driver of deforestation there. Counted 10% of forest loss, while pasture is the larger driver. And average time lag between forest loss and soil cultivation was about 4 years. Central Asia is a big part of the program, has been for some time. We had regional meetings in Urumqi, starting with Urumqi, China, 2007, and we had a regional meeting in Almaty, Kazakhstan, then in China, Kanfeng, and Tashkent, Uzbekistan. As a result, we had these publications here, and Professor Fennebury will give a talk. This conference. He is a leader of the Central Asian Network, providing regular seminars, webinars, so anybody anywhere in the world can join in and listen in. Based on the results from the program projects paper published in 2020, a book published in 2020 about drylands over Greater Central Asia, set of various publications, contributing authors, not just United States, but some European and Central Asian collaborators. What was happening in Central Asia? This looks in 1950 was a Russian, Soviet pollster. Don't stay behind. Let's give our motherland 3 million tons of cotton. Cotton production was the goal of it. But cotton is a very thirsty crop. This is what happened when two rivers, Amur Darya and Sir Darya, that were going into Aral Sea, were diverted for irrigating those crops. And this is an example of poor land management in the former USSR, shrinking the Aral Sea to a quarter of its original size. Consequences were wildlife, human life. These images from Lancet. One is from Lancet 2, and then Lancet 5. And you can see how from a regular normal size that you can see on the geographic maps of 1970s and 80s, now it's shrunk to some remains. Actually, they distinguish between the southern sea and the northern sea. I'll show you the difference. But this lack of water sustainability led to serious changes, both in hydrology and biodiversity. So water inflow dropped, water level dropped, even numbers there, like 70% down by volume. Aquatic surface reduced, and biodiversity species decreased substantially. But there were also social changes, population migration, and health damage, various reduction of length of human life, worsening of the living condition. This is the picture of the boat that is sitting on the ground. It needs to be water. They tried to save the northern part of the Aral Sea, North Sea, by building a dam there. It was called Aral Dam. They gave up on the southern sea because it was desiccating and probably not much could be done. But northern sea seems to be preserved. This is an image from a Japanese sensor instrument, ALOS, Avenir, 2006. We've had we talked about different processes in terms of degradation. I think that the name of this conference used to have the word degradation part of it, and now it's desertification, desert, and violence. Degradation is it, but I thought that it would be good to show the degradation in Central Asia. You can see salinization, waterlogging, salt dust, and this is the from the project by Xin Shi. Here, no, he's not here, but he's at the conference. He's from Michigan Technological Institute, participating in this conference. What is known that the losses from land degradation in Central Asia amounted to $6 billion United States dollars, really, and is observed the extensive, ranging from 4 to 10% of cropland, 7 to 68% of pasture land, and 8% of forest land in each country. The integration of the processes that are happening in RLC was trying to be integrated by Irina Sokolik and Georgia Tech. As you see, the models for biological model, land model, and the dust model here. We have also a project that Kirsten DeBerge from West Oklahoma, who just moved to Wageningen University of cropland to urban loss in Uzbekistan. Okay, and I don't have much time to go on this, but salinization is a big problem about how they irrigate land surface. When we traveled in Uzbekistan, we saw snow on the field. It wasn't snow, it was salt, white fields. And it's probably my last example is from Michigan State University, Levi, looking at crop field object extraction semi-arid area where they used very high resolution world view to gauge how to drive it. So that's an example for Asia in Mongolia, China. And also we have a Kazakhstan and Mongolia project by Jichuan Chen of the Michigan State University. The areas where it's done, I think they show the difference between the results in Mongolia and Kazakhstan. In Mongolia, they had the special agricultural redevelopment 2005-2009, whereas in the Soviet Union, there was a virgin land campaign. That was in 1960s, so last century. Thank you very much.
Well, thank you, Garik. We are running out of time, so we will move to the next presentation by Garik Gutman. And if there are any questions later, please contact Garik later.
Can you hear me? Yeah, okay. So I'm going to try to give a brief presentation on climate data record for land and long term, and specifically from polar orbiting Earth observation satellite. And I just put the name of my colleague, Chris Justice, was also, my mentor during my postdoc, but there's many other people who participate to that research. One is in the room here, Gary. I mean, I work with Gary. Anyway, I'm not going to start talking about little story because I just want to give you a little bit of my story and I came to work with that. So what's land climate data record? I mean, when we talk about climate, we talk about data set who span over decades. I mean, at least 2, 3, 4. And with the remote sensing, when you're looking at climate data record, I mean, you have to deal with several instruments and several sensors. Here is what we had, and AVHR was mentioned. Also, the MODIS and AVHR is continuing. After the MODIS launch, you have that some French instrument. You have the continuity of the MODIS into the beers with NPP, from NPP, J1. J2 was recently launched successfully. And the European side are not, doing nothing with the Sentinel-3A and 3B. And that's just about course resolution. There's another data set that was mentioned, very useful, like a Landsat, and I'm going to talk a little bit about it. And what's important with the climate data record is that we have to have consistency in the data set. Otherwise, you're not looking at climate, you're looking at your instrument, varying with time. And you cannot just simply adjust one to the other. It's much more complicated than that. So I think it was mentioned already, but people talk about atmospheric correction, very important point. Calibration. Calibration is the most important thing, in my opinion, because calibration will determine automatically what's your stability. So here is one of the problem child of remote sensing, AVHR. When he was young, or the data set was young, he was very problematic. It's like a 3 or 4 years old, or terrible tools. And hopefully, I'm going to convince you that he improved with age, which is not the case for everybody, but anyway. So, and also something important is a BRDF correction, which was just touched on, but with polar large field of view satellite, this is very important. Also, people tend to forget that the sun also plays a role. So you can have seasonal variation that just induced by sun variation. And I don't want to get into this debate, which was a subject to numerous publications about the seasonality of the Amazon forest, if you know what I mean. But anyway, it was there. And also I want to mention the stratospheric aerosol, which actually gave me a job when I started at NASA. And I'm going to get back to that. I'm going the wrong way. Yes. Something we tend to forget about is that the importance of having accurate geolocation. And just back to the AVHR in the early days, 1981, and this is from Jim Tucker, who discovered the 3 cities of Dakar. So on 3 different days, Dakar moved by tens of kilometers, which is not a good thing when you try to do, monitoring in time of something. And also something, maybe this is not known as well, is that AVHR has a clock, which was obviously not very accurate, and which was drifting with time and reset at, a regular interval. But the lack of transparency about this, that if you didn't know about it, and not a lot of people knew about it, you will look at your geolocation and you will move by 1 pixel every time. They reset the clock and, but this was accounted for later on, of course. So let's get back to the stratospheric aerosol, because I was working with Jim Tucker and has this, and Brent Holben, and they have this wonderful idea of, and also Garik, of compositing the data and get rid of the atmosphere, which work in a good way, except when you got a stratospheric aerosol correction, then you can composite whatever you want. You will not get rid of those aerosols, stay in space for years. So I got a job to do that correction, and this was just the right time. So this was the picture of the eruption. And recently, 5 years ago, we went with Garik here, you recognize with his hat, and Chris Justice to verify, what we emphasize about the, size of the eruption. Anyway, and going back to, this eruption, I had to do corrections, so I had to derive the aerosol optical thickness from AVHR itself. And at that time, I didn't discover, because we knew about it, but there'd been a sizable eruption by the El Chichon in about 92, if I remember correctly. So that was also part of the data set. And we were able to use AVHR itself and validate, and I don't have time to go into too much detail here, but we were able to retrieve the optical thickness from the stratospheric aerosol, compare back to the safe data, which is the direct measurements, occultation measurements of the stratosphere, and do several kinds of things. and then validate the correction. And just to show you the impact of the stratospheric aerosol, and this is on the stable side. This is forest side. One is in Australia, one is in California. And you could see here the red signal compared to the blue signal, which is corrected. But we have a very sizable, I mean, this is like a major, at this spatial resolution, it's kind of a big deforestation or major droughts in the data set. So you really need to be careful about that. So the atmospheric correction that we developed originally for AVHR evolved, and I don't have time to go into detail, but this is work which started, you could see 94, and it's still going on right now. We're still working on it. We're still improving. And a large part of those improvements is, of course, due to the launch of MODIS on Terra Aqua. And that's very good news. That means that, you get better sensor. You're able to go back in the past and improve the record, which is, a very interesting point. So here we now have an algorithm. We originally produced AVHR, MODIS, VIRS, and we have in development Sentinel-3 product because, as you know, the MODIS sensor may stop next June 2023. There's a real possibility that the record will stop. So better get ready. I hope you all know how to use VIRS data. Anyway. Sorry. So this is just where we apply our atmospheric correction algorithm. So I mentioned already several sensors, but I want to say that we also use it on Landsat, OLI Landsat 8 and 9 now, and MSI on board Sentinel-2. And this is a generic algorithm which takes care of the consistency part because we have a traceable relative-based approach that we can apply to different sensors, and which is error budget driven and also validated. And this is just the generic approach. I don't want to go into too much detail, but the key is that you have certain ancillary data that you could derive from, from model run or things like that. And you have, most importantly, the derivation of the aerosol optical thickness at the pixel level. And that's very important. Otherwise, you're really stuck. This is just the basis for last source, the atmospheric correction, based on radiative transfer, which was validated to better than 1%. And as I say, inversion of key atmospheric parameter. For the validation, I tried to validate the surface reflectance early on, and we tried to validate, we have instrument. I tried to go to the field and measure, and I just gave up at that point, especially with MODIS 250 meter pixel at the best. I had to run very fast in order to collect enough measurement during the overpass time. And since I was not ready to do that, I just, went to an indirect approach, which was to use the data from the AeroNet network, which measure aerosol and water vapor very accurately, and radiative transfer, which are able to do atmospheric correction with the most precision, and derive what I call the reference data set, which is like the best correction you could make and compare to the operational correction. So with that, we got millions of samples and several millions of samples. This is like validation result of one of the version of the MODIS surface reflectance called collection 5. And this is the red and the near infrared. And we derive, not only error, but error in terms of accuracy, which is the bias, precision, which is the repeatability, and uncertainty, which is the combination. And this is collection 5. So from 2000 to 2009, over 200 AeroNet sites. And when we improved the algorithm for collection 6, immediately you could see, those errors going down. And this is actually the specification. So it goes way under the specification, which is very good news. So that method enables to track improvement in the product. Go back a little bit to the LHR calibration, and we start working early on calibration, and I was working with Joram Kaufman. 2 minutes, okay, and we did some calibration. We were about 4 to 5% accuracy, and then we continue when we got modis. We intercalibrate. I don't have time to go into details, but people collect from NOAA also intercalibrate on the moon, and we improve the calibration. And then we got into a full-blown method where you use MODIS as a cross-calibrator, but over 400 sites, and we were able to demonstrate by using VIRs that we could get calibration accuracy for VIRs or stability monitoring up to plus or minus 0.5%, and improve LHR to plus or minus 2%, which is actually the spec of the best sensor today. So that was very good news. We also are doing through the cross comparison some spectral adjustment of the LHR. I don't have time to go. We improved the cloud mask over the years. We improved the BRDF correction. We cross-calibrate also with Landsat to go back in time with a better quality sensor. What's going on? And we improved the water vapor retrieval and the LHR based on the MODIS data, and went back and derived a surface albedo from LHR that we compare to MODIS. Very good. We also, the method we developed for MODIS for agricultural monitoring, and this is the yield prediction over the United States, we applied over LHR over the full record, and with a reasonable accuracy, I would say. And finally, some of my colleagues at University of Maryland, they used the whole LHR record from 82 to 2016 to look at forest change. And they derive very interesting results, which are actually counterintuitive and were published in Nature. So the day I saw that, I was like, man, you could use that data. This is really something that pleased me. So conclusion about this talk is that, the climate data record is a full record, and the data are always alive. You can always improve them. And we need overlap emission as long as possible, so you can tell NASA that they need to keep it up as much as they can. Thank you very much.
Thank you, Eric. And again, please contact Eric later for more questions. We will rapidly move to the presentation.
Okay, so we changed the subject a little bit. Until now, we talked about things to do with satellites and big stuff, and we're gonna do a little bit of a shift. So today's talk is all about the dynamics of soil erosion and how it's affected by rain. And we're gonna do that using model for soil erosion and another model for deriving rain change listing, right? My age. Not this. Right, here you go. Okay, so was mentioned here before that the soil erosion is a big and alarming or undergoing alarming rate of change. There's a lot of soil erosion. You can see here some numbers. And some of it is either driven by or driving soil degradation, mentioned here before again. Some of the organic matter changes, surface salinity, compaction, salinity, and you name it. Now, since there is a big problem, there's also a big need for finding either ability to foresee it coming, so we can take measures against it or to stop it from happening. This map was shown, or similar map to this was shown a little bit earlier. This map shows soil erosion worldwide. The gray areas are the areas that we have no data. It's not that there is no soil erosion, and you can see the yellow blotches everywhere. And this brings us directly to the map that, remember who one of my previous chats talks has shown. And what you can see here that when I looked at it the first time, I saw, okay, all these blotches go very well with cropland. So, it's related. So now that we've said that soil erosion is our problem, we are looking for ways of being able to either knowing when it's happening and how much is going to happen. There are models that help us do that. These models are, if you put data in them, will tell you which areas are likely to be eroded or degraded. Right? Okay, so we chose, there's two main ones, two key models. One is Russell and the other one is Muscle. Sorry, it does sound a little bit like a rhyme. So we chose Russell. That's why it's in all these points here. Mostly because it's very easy to use. It's intuitive because it's in a sense cumulative. It's simple. It's easy to parameterize, and it works pixel by pixel or written here cell by cell. And what it's like, well, the Russell itself, what should be here instead of the word Russell is the risk of soil erosion. Okay, so just imagine that this says soil erosion, and it's made of a few factors. All of them are brought into the database with in a pixel type data. And these are the 6. I will go over it in a second, so I'm not going to stop over here. But what I do want to say is that just like other types of models, we use only one input, but actually we can break it up into more parts and look into the making of this parameter that we're going to use. So the first two parameters are all to do with topography. They're both derived from DEM. This is a DEM. DEM is a digital elevation model, and it basically tells you for every pixel what's the height. So from that, you derive two different outputs. One of them looks at for every pixel, how many pixels are contributing water to that pixel. So it's cumulative. You can see it here. That's why you see the river bed here, where many pixels effectively accumulate. And this one is the slope. It basically tells you for every pixel how steep it is. The second component is the factor of K. It's all about what kind of soil is in that pixel. And as you can see here, it's fairly easy to determine. It ranges between 0 and 1, although vast majority of K factors are between these two numbers. Actually making the number is based on a bunch of other characteristics, some of them physical and some of them chemical. The next parameter that we add to this model is actually made out of two. It's C, the P, and P. C and P I'm going to join together. C represents the land cover and management. That includes vegetation, that includes agriculture, that includes other human impacts and natural impacts for that matter. And P is actually kind of a sideline of sea, and it's all about support practices. Like in Israel, we've got the sheikh, the system of stopping the degradation of land. So that I'll get back to this in a minute, but I'd mention it. In any case, CNP are usually bunched together into one factor. So now we actually got 3 key factors, and the most important factor is R. And I'm going to stop here for 1 second just to say that the factors that we've talked about until now, they're very slowly changing. They change very slowly, rather. Okay, so you've got the soil is not going to change very quickly, not from year to year. Slope is not going to change from year to year, but rain can be completely different between 1 year and the next year, and that's why it's becoming the key factor for measuring your erosion. And it's done in 4 steps. First, you decide that you're gonna work. You need to define a storm. The storm starts and ends. You basically find out when the storm starts. Usually 6 hours without rain, or 6 hours with very little rain, or something like that. And the same on the other end. Then you measure how much energy has landed on that 10 minutes of time. And from that, you sum up all the 10 minutes that lead to give you the amount of energy that this storm has brought to that pixel. And lastly, you sum up all these to have the yearly energy that fell on a single pixel. And it usually looks like that. This is a gradient. You can see that on the west, it's got much more storm events than on the left, something like that. Okay, so we talked about rain, so let's talk about Israel a little bit for those of you that are not from here. We'll start from the left. This is a map taken from kind of atlas. I don't know, some of you my age maybe know what atlas is. But now that you don't have atlases, you get things like this, which is this map of average annual precipitation comes from a model. So this is measured. This is from a model. A little bit about the geography. Most of the rain comes from the northwest. Then it hits a line of mountains, which is the reason why you've got this projection here, and it obviously translates into vegetation straight away. Okay, so very quickly, we used a model called WRF. I'm not going to stop on here. Called WRF to actually look and project the change in rain for the next 15 years. So we started at 2006. Oh, no. So we used WRF. I'm going to skip all the rest, but I'm going to say that we ran it from 2006 and 2036. So some of it is already happened, and some of it is or will happen. It's at 6 kilometers for every pixel. This is very small for this kind of model. And it's 30 years of precipitation at 10 minutes intervals. A lot of data. So the reason why we do all this is we want to quantify the erodibility of soil based on rain, either for real or something that is made from a model. And with that, we can actually project what will happen in the future in terms of erosion. Sorry. So we used a case study. It's called Habsor. It's one of the larger basins in Israel. It borders on the Mediterranean, and you've got the sea here, mountains over here. This area is desert. This area is full of agriculture and lowland. We used some model that we've made in Google Earth Engine to create a classification map, and from that we got the C and the P. That's the practices. If we have a K factor from a geological map, we have a DM which produced LNS factors, and we start with one R factor map that was made from 2020. And this is what it looks like. You can see that this area has got potentially a lot more erosion than this area here. This is, by the way, a desert, and this is a lowland with a lot of agriculture. Okay, so we also wanted to see what's going to happen in the future. So this model was made from this is the R calculated from all the data collected in IMS stations. That's how much precipitation is per 10 minutes since 2001 and 2020. And from that, we extracted this area here, which is our basin. And I don't even think I've got time to show the film, but if we compare it, you can see that the averages or the amount of storms you get in the different areas, or not in the different areas, but you can see that this is changes differently to the entire country. I'm not going to stop over these, but you can see. Here's 1 second to see a little bit of moving pictures. The top one is a model that is considered to be very has a lot of rain, and the H is a conservative. So one is exaggerated and one is conservative. You can see here. I'm not going to stop on all this, but what we can see is that if we see that the red is real, then you can see that actually the C model, the one that we consider to be exaggerated, seems to work alongside the reality. You can see that in the first couple of years, it actually gives more or less the same picture, and then the model kind of takes off on a different tangent. That's one of the things we know about models. Not going to stop here either, but what I am going to show here is that if we look at the data for the years that are covered also with the stations, we can see that the C model actually looks more similar to the model. And then we can also see that the models behave very differently for the future. So if we decide that this one is more real, then we should look at this if we want to see if there is going to be erosion in the future. And this is from hot from this morning. Even my colleague and boss here has not seen it yet. So this is, I've taken 2 years, one with a lot of rain, one without rain, and this is what it looks like when you have a lot of rain or very little rain. That's it. Actually, it is a film, but sorry about being slow on the
Thank you very much, Tamir. And we will do the last presentation in this session. Tarin will be here again.
So now you're going to see a lot of nice picture of flowering phenology of almonds. This is part of the presentation. This work, basically what we wanted to do is to look on the winter tree phenology, and we developed a model to forecast the orchard blooming time and yield. This is a joint project with Maciej from UC Davis and Or Sperling from Vulcani Center. And this is a project that Oren, which is sitting here, is his master degree. So there's a lot of people involved in this very interesting project. So I will start by saying that temperature is one of the most important parameters for blooming time. And the dynamic of vegetation phenology is something that is a well-known parameter that is affected by climate and affected by temperature. And it's of course mostly affecting deciduous trees, which need specific chilling hours to have the signal for flowering or to have the signal for blooming. So one of the issues that we can see today due to climate change is that the temperature is changing, but the temperature is changing and rising, but it's also important when they are changing and rising, and mainly in the winter. This is something that we usually not taking a close look, but in the winter, if we don't have enough chilling hours, so part of the deciduous tree will be affected, and then their blooming won't be synchronized. Usually the yield will be much lower, and it will affect, of course, a lot of aspects related to crop production. And in this case, we're mainly focusing on almonds, which is a very important crop in California and other parts of Vermont. So just to look on the mechanism, so usually when we have the phenology of the flowering, so the flower is supposed to have a specific chilling requirement, which those chilling requirements will signal the plant to the bud breaks and to flower. And after there is a period of time that we need a higher temperature, so the flowering will be synchronized. And if we don't fulfill the chilling requirement according to the needs of the specific tree, so then probably what we will have is a very, very low yield. One of the mechanisms that control this process of the flowering phenology is the non-structural carbohydrates, which is the energetical and metabolic source of plants. And in here, what you can see is the dynamic of the non-carbohydrate mechanism. You can see that we've got here the starch and the soluble sugars, which are two components that related to the non-structural carbohydrate. And what you can see in here is the dynamic usually when there is no leaf, so there is no photosynthesis. So usually what you will have is you will have a reduction in the non-structural carbohydrate. And once the tree is starting to use its energy until it doesn't have any more energy, and then it's a good signal for the tree to start leafing, starting to do photosynthesis, accumulating additional non-structural carbohydrate. And this process is a synchronized process that we can see. This process is also highly dependent in temperature, which reacted the enzymatical processes of those deciduous trees. So our colleague, Maciej, thought that it's a very important parameter to follow, and he established the Carbohydrate Observatory, which is an observatory that collects data for more than 400 cropland in California. And basically what he do, he collect barks from trees from different locations in California and do the analysis of non-structural carbohydrate and use this to develop model of how to manage those cropland. So we've got a large amounts of data for the past 3 years from 400 different plots from California, from entire California hill. Next, what they did is they used those dynamic carbohydrate dynamic to try to develop mechanism processes to link between the carbohydrate concentration and temperature. And the model name is carbohydrate temperature model, which basically what they did is they use an hourly temperature dynamic, accumulation of hourly temperature dynamic, and they relate it to the concentration of non-structural carbohydrate and parameterize the model. And based on this model, they had the ability to predict flowering or blooming time for the different crops. Now, when we've got a nice model, we need to validate it. And one of the issues is that we need to move from a specific plot regional scale and to have the ability to link between this model, parameterize this model, and to also look on those processes at the regional scale. So the objective was to apply the city model at a regional scale for predicting current and future blooming dates and in related to winter temperature, and of course it's also related to prediction of climate change, which of course could assist us in detecting a blooming time and maybe detect areas that are relevant for a future orchard plantation. Additional objective was to develop a remote sensing-based platform to detect blooming time in the deciduous crop tree. And of course, we integrate the remote sensing and the city model, see if those are saying the same or predicting the same flowering phenomena. So we're moving to the remote sensing part. So when we're looking on a spectral signature of a flower versus leaf versus soil, you can see this is a white flowering of almond. This is a paper published by Jim. You can see that there is a clear signal, different spectral signal from the leafing, from the flower, and from the soil. And we can use this spectral, very different spectral signal to develop indexes, and this is what Chin did. He developed the enhanced blooming index, which basically what they do is they're taking the brightness, the greenness, and the soil signature to detect the flowering phenology, and they had the ability to show very accurate result of the flowering phenology based on the planet scope and based on the sentinel. Next, additional approach was used to take this EDI, which is an index to predict flowering, and they use a chlorophyll index. In this case, it was the green and EDI, and the variation between the signal or the phenology of those two indexes can give us, based on change vector analysis, the peak of the flowering, the beginning of the flowering, and the end of the flowering phenology, which is something that is very important due to climate shift. So if we've got climate shift and we've got a very warm winter, so what we will have is we will have a very early flowering signal versus the much cooler winters, and then the flowering phenology will shift and change. Additional very important aspect, mainly in almond and deciduous trees, is that they need the two cultivars for pollinating. And once we have two cultivars, so we need to have synchronize between those two cultivars. So the approach that we developed is basically developed based on the PRISM data, which is a long-term historical data of temperature. The data that we've got here is minimum and maximum temperature, and we use this data to derive 10 hourly temperature. On the hourly temperature, we validate the city model, which is based on the carbohydrate data that we collected and based on the mechanism that link between carbohydrate concentration and temperature. On the other hand, what we did is we developed a way to validate flowering phenology. We did it with several tools. So we started with time-lapse cameras to look on the phenology that was located in different orchards in California and in Israel. Then we used drones to validate the information that we've got from satellite. And then we use a time series analysis that is based on Sentinel in this case. And we had a long process that I will show in a sec. So this is an example of the red area, the red points that you can see here are almond orchard in Israel. The almond orchard that we selected are marked here. We put a time-lapse camera in each one of those orchards. In California, it looks with a massive amount of orchards. So California is one of the main area of almond growth. You can see the blue dots, those are the time-lapse camera locations. So there are several time-lapse cameras that we applied. And you can see how it looks like. This was in 2021. And one of the nice thing here is, I don't know if it's nice, but you can see that there is mismatch between the two cultivars. One is green and the other one is flowering. So this was a very, very hot winter. And once it was a very, very hot winter, we had a mismatch between the cultivar and the yield was very, very low. This is something that we can capture from those time-lapse camera. We also use those time-lapse camera to detect the specific timing of the peak of the flowering, the maximum flowering phenology, and the end of the flowering phenology. So here you can see those are 4 sites in Israel, and you can see that there is a very big variation in the flowering time. You can see that there is differences between the different cultivar. The 2 cultivar that are usually planted in Israel is El-Fachem and 53. Those are the name of the cultivars, and you can see that there is something about 10 days differences in warm and winter where those are mismatched, and usually when we have a very warm winter, so we have a very low yield due to that. And in here you can see that the comparison that we did between the city model and the blooming peak based on the cameras. And one of the things is that at the beginning, the city model wasn't synchronized as well as we thought that it will be. And then we tried to start parameterize it. Additional thing, I will go back to the city model in a sec. Additional thing that we do is we use UAVs, which we have the ability to have a very good and very accurate assessment of the flowering phenology with the cover of the flowering. And in here you can see the differences between synchronized phenology and unsynchronized phenology. It means that we've got rows that are with flowers versus rows that are usually in a mismatch with the other cultivar that they need for them. We did a lot of analysis that related to carbohydrate concentration in those trees. And we did assessment of the leafing phenology and the percentage of the leafing also from the ground. You can see how it looks like when we're looking on the phenology of those different orchards. One of the interesting things that we did is we applied several models that was already available, like the dynamic model, which is taking the dynamic temperature or the accumulation of temperatures. And in here, what you can see is this is the dynamic model based on 2019 and 2020, but in the warmer winter, you can see that the accumulation of temperature was relatively low. And the flowering started just when we had a stop in the accumulation. It was a very warm 2 or 3 days, and then it created a peak in the flowering of those trees. And you can see that there are differences between the 2 cultivars, the El-Fachem and the 53. And this is an example of how it looks like. Next, we move to the satellite data. And in here, each one of those, you can see this grid. So each one of those pixels represent an EDI index. And what we did is we correlated between the EDI index based on satellite versus the EDI index based on drones. You can see that there is a relatively good match. And the reason that it's not 90%, that we've got mixed pixels, as you can see in here, which affecting the ability of accurate detection between the drones and between the satellites. Next, we move to California. And in here, the problem starts to be much more complicated because this is a very large area that we need to capture the information. One of the big problems that we had was clouds, that we need to mask those clouds. In here, the cloud mask that Oren developed. The other issue that we needed to solve was the detection of the orchards. So in here, we use the NASA USDA model of crop detection, which they've got a crop detection from the 90s. So we use this crop detection map to detect the specific area where we've got almond orchard. And then we apply the EBI and the NDVI index. And you can see here the variation in the phenology. And based on the change vector analysis, we can detect the specific blooming time for each one of those orchards. So in here, I think that the most interesting part is to look on the variation in the landscape. And in here you can see for example, the year 2022, you can see the starting of the wave of the phenology, and then you can see the variation during the winter, and at the end you can see the reduction in the flowering phenology and the end of the flowering time or the flowering period. Next, what we did is we applied the city model, which is taking the prism data, apply the prism data to develop a prediction model of blooming time. We use this data from prism model to predict the blooming time for the past 40 years. So it means that once we have a good temperature data, and once we've got a city model which is parameterized, we can detect the specific time of blooming for different cultivars. In this case, we use it to detect the flowering phenology of almonds. And then we wanted to validate this model with remote sensing data. And in here, you can see the result of the comparison. So this is something hot from the oven, as we say. And you can see that there is a very nice match. Sometimes we've got a mismatch and we need to, again, parameterize the city model. We'll have the ability to detect with a very high accuracy the flowering phenology and the timing of the flowering phenology. Once it will be parameterized, it means that you had the ability to look on areas that are relevant for flower, for specific plantation. We can detect area that could be in risk due to high temperature. We can use a prediction models of what will happen if we'll have different scenarios with different temperatures. So to conclude, we developed a diagnostical approach based on seasonal change of carbohydrate and temperature. And we try to look on different parameters related to management, to cultivar, genetics, and additional parameter that I didn't get into as age and farming practices. We had the ability to use remote sensing data with several very nice approaches like the EBI and NDVI and change vector analysis, detect the peaking time of the flowering phenology. And one of the main things that we found is that in California, we've got a large variability between the plots, but the plots were relatively synchronized, the cultivars were relatively synchronized, versus the cultivars that we've got in Israel, which are in a mismatch when we've got very high temperature. And one of the things that we understood is that the cultivars that were planted in Israel are not suitable for good pollination due to the climate effect that we can see now. So that's it, and thank you.
You used the NDVI value. Did you also consider the saturation with NDVI?
Yes, so that's here, so I have it. So yes, we applied also a saturation detecting of saturation. So we'll have the ability to detect specific area where we've got like anomalies of information that are not correct. And we removed all of those anomalies. We smoothed the spectral signal of the phenology. So the phenology will be based on Spitsky-Golomb. We did a lot of processes that was needed to take care of the data and to have accurate data, or also to look that we are looking on almonds or other orchard. There is a long process of fine-tuning the data so we can.
Another question.
I wonder about the scale up from the drone data to orbital. It's very interesting. You mentioned a mixing might be one cause. And I was wondering, because the canopies are 3D, the side of them is illuminated directly and the side is diffusely illuminated, and the drone kind of compensates for it, but the Sentinel doesn't.
Yeah, so there is a lot of issues. Again, drones, we're working a lot with drones. They've got a lot of advantages, but also disadvantages versus satellite. That they've got a lot of advantages and disadvantages. I think that the use of drones to apply unmixing is very important. This is something that we're developing in my lab. So we're using drones to detect the proportion of different land cover and use it to validate the satellite data. But overall, with drone, it's something that you can cover a large area and to know the proportion of the flowering before. So,
Thanks, Tarin. Are there differences between cultivars, first in Israel and then between Israel and California in the length of the blooming period?
yes, so
Because long cultivars can be used like, I don't know, kind of insurance or guarantee or more overlap.
So in California, the variation between they've got several cultivar Napa and other cultivars that we don't have in Israel. Usually they are highly synchronized. Also in warmer winter, the variation range between 2 to 4 days in most of the area that we worked on. We've got several plots in the past 3 years. In Israel, what we found is once you have a very warm winter, there is very big mismatch between the cultivars that we planted in Israel. And then the question is, first of all, what to plant in the future. And this is something that is very important. Which cultivar will be more suitable for the temperature that are probably rising. And the selection of those cultivars might be cultivars that they don't need pollinators. And those cultivars will be much more successful in a region like in Israel. So there is a lot to do, but it's something that is very interesting to do.
Thank you very much, all the speakers, all the audience.